Here we want to prove that the limit as x goes to 1 of 8x plus 5 is 13. And first, it's helpful to note that this is obviously true. If we, for instance, plug in 1 for x, we can see that this limit quickly evaluates to 13. So we can see that it's true, but how do we prove that it's true mathematically? Let's use the epsilon-delta definition of the limit to prove that this is true. Okay, so the limit as x goes to a of f of x equals L means that for all epsilon greater than 0, there exists some delta greater than 0, such that if x is within delta of a, then f of x is within epsilon of L. So what this right arrow means is an if then. If then. And when I say x is within delta of a, the way we say that mathematically is to say the absolute value of x minus a is less than delta. And then we say that it's not equal to 0 to say that x never hits a. Then, of course, we say f of x is within epsilon of L. The way we say that mathematically is absolute value of f of x minus L is less than epsilon. So don't be too put off by this definition, right? It's just good to see rigorous mathematics and to see what's happening behind the scenes of the limit. But I've seen students just get paralyzed when they see this and their brain just turns off. Don't worry. I think you'll find that these proofs are actually pretty approachable. The proof itself follows a very distinct process, and to remember that process, you really only need to remember 4 things. Given, choose, suppose, check. If you can remember those 4 words and the basic structure of the proof that those words provide, you'll find that this falls into place fairly nicely. So let's do the proof. All right, so we write the word proof. Proof. Okay. All right, given. So we say given epsilon greater than 0. So what I'm saying here is you give me any epsilon greater than 0. We can then choose some delta equals to, I don't know what. That'll come out in the problem. But delta equals something. So we'll leave that blank for now, and then we'll go back and fill that in later. Okay, we're making progress here. Next we say suppose. Suppose what? Suppose that the absolute value of x minus 1 is then less than that delta. But we don't want x to be equal to 1, so we'll also say that 0 is less than that as well, so they're actually never equal. Okay, so there we have our given, choose, suppose, and lastly we go with check. Okay, so checking that. What do we want to check? Well, we want to check, so we're supposing this part. This is our suppose. And we want to check that the second part is true. So let's check it. So we have f of x minus L. Well, in our function, let's make sure we're okay with everything in the function. This x approaches 1, so 1 is a. This thing inside the limit is our f of x. And this 13 on the other side is our L, just to see where everything fits into this definition. Okay, so our check is we do the absolute value of f of x minus L. So we have absolute value of 8x plus 5 minus 13. 8x plus 5 is our f of x. And minus 13, this is minus L. So 13 is our L there. And then we get to work manipulating this bit here. So we want to manipulate this until we get an x minus 1 essentially to come out somehow. And this will always happen if you at least do the right mathematics on it. So let's see. We have, how about absolute value of 8x minus 8, which we can then factor an 8 out of. So we have 8 absolute value of x minus 1. And there we have it. Now eventually we want to have this equal epsilon. That's our goal. So we need to work it so that we somehow get an epsilon at the end of this thing. So just keep that in mind. That's what we're heading towards. Well, okay, we have x minus 1 is less than delta from this step up here. So now we can say this is less than 8 delta. But remember, we want this thing to end with epsilon, so let's let delta be epsilon over 8. So right there, that step right there where I said, okay, I want to end, and then we have epsilon for our end, our very last thing here. So right here where I said, okay, let delta be epsilon over 8, that's where we go back up and plug it in here to our choose step. So I'm going to go all the way back up. I'm going to erase this blank line here and put in epsilon over 8. Okay, and that completes the proof. Our 8's cancel right here, and we are left with epsilon, and we've completed the proof. Usually put a box of some kind. Maybe you fill it in, maybe you don't. Some people write, if you're really fancy, you could write QED. That's what they used to write back in the day at the end of proofs. If you read some old Newton or something like that, you can put a triangle, a circle, some kind of notation to say, I have completed my proof now. So let's take a look at this. What have we done? Let's see if this makes a logical argument. We've said given, let's go back up a little bit here. So given any epsilon greater than 0, so okay, we're good for all epsilon greater than 0, I can choose some delta equal to epsilon over 8. So what this is saying is no matter how small of an epsilon you give me, I'll choose a delta that's even smaller. I'm going to do epsilon divided by 8. Okay, so there exists a delta part. Now such that the if part is this suppose. Okay, suppose that absolute value of x minus 1 is less than delta. So it's very close. Our x is very close into 1 is what that's saying. And then this check is our then part of this implication here. So then we just make sure that f of x minus L is indeed less than epsilon, because that's what we need to have here to complete the proof. And we follow it down, right? This 8 factors out. We get to x minus 1, but we know that x minus 1 is less than delta from over here. So that makes this less than 8 delta. And then we know that delta is actually epsilon over 8. So then we replace delta with epsilon over 8, leaving us with epsilon, which completes the proof. And that is how you prove a limit for at least a nice linear function.